We live our lives on a stage made of space, and inside a story that flows through time. It feels totally fundamental, right? Absolutely real. But what if it's not? What if the very fabric of our reality, space-time itself, is actually just an illusion? Something that emerges from a reality that's far, far stranger and deeper. Well, modern physics is basically telling us that our most basic intuitions about the universe might be completely wrong. And we're about to find out why.
And you know what? This feeling is not new at all. Almost 1700 years ago, St. Augustine just perfectly captured this essential paradox of time. We feel it, we get it, we know it, but the second you try to grab it and explain it, it just slips right through your fingers. This ancient puzzle has now become the central battleground for our most advanced theories of the cosmos.
So before we can really get our heads around why physicists are starting to think time might be an illusion, we got to take a step back and look at the classical debate. For centuries, philosophers have been wrestling with a really simple question. Is time a feature of the world out there that we just discover, or is it a framework that's built inside our own minds? And this question basically created two opposing camps. On one side, you had Aristotle. He argued that time is fundamentally tied to change. I mean, it makes sense, right? We see things move, the seasons change, and from all that observation, we get our concept of time. We learn it from experience. But on the other side, Immanuel Kant proposed something way more radical. He said time isn't out there at all. Nope. Instead, it's like a pre-installed piece of software in our brains, a fundamental lens that structures everything we perceive. We don't learn time from experience. Experience is only possible because we already have the framework of time built in.
This whole debate raged for centuries. But then, in the early 20th century, a patent clerk named Albert Einstein didn't just join the conversation, he completely flipped the table over.
Einstein's theories of relativity showed us something incredible, that space and time are not separate things. They're not independent concepts. They are intrinsically, fundamentally linked. They form a single unified entity, a four-dimensional fabric that we now call space-time. The crazier part, the faster you move through space, the slower you move through time. They're really just two sides of the very same coin. Einstein's old professor, Hermann Minkowski, really captured the mind-bending implications of this perfectly. He realized that space and time, as we individually perceive them, are just shadows of this deeper four-dimensional reality. They're relative. They literally change depending on how you're moving. And this leads to an absolutely crucial point. While you and I, if we're moving relative to each other, might disagree on the distance between two events or even the time that passed between them, we will always agree on this space-time interval. This interval is the new absolute. It's the true, unchanging distance in this 4D reality. This was a massive shift in our understanding, but it also, funnily enough, set the stage for an even bigger conflict. Because as unbelievably successful as Einstein's vision was, there was another revolution happening in physics at the very same time. And it turns out our two greatest descriptions of the universe would be completely, fundamentally incompatible on the nature of time itself. Okay, so we've got general relativity. This is the theory of gravity, stars, galaxies, all the really big stuff. And then we have quantum mechanics, the theory of atoms, particles, and fields, the super tiny stuff. And here's the kicker. Both of these theories are spectacularly successful. They are pillars of modern science. The problem is, they treat time in completely, totally different ways. The contrast here is just stark. In Einstein's universe, time is part of the system. It's a player on the field. Gravity can literally stretch it and slow it down. Your clock and my clock can tick at different rates. But in the quantum world, time is more like the stadium clock. It's rigid, absolute, a background that just ticks away, the same for everything, everywhere. It's external to the system. So one is dynamic, the other is static. This massive contradiction is what physicists call the problem of time, and it's probably the biggest roadblock in physics today. So what happens when you try to force these two theories together? When you attempt to write a single equation for the entire universe, from the quantum to the cosmic, well, you get a result that is so bizarre, so strange, it suggests our entire experience of time's flow is nothing more than an illusion. Back in the 1960s, two physicists, John Wheeler and Bryce DeWitt, they went on this quest for the ultimate equation. They wanted to combine the principles of quantum mechanics and general relativity to describe the quantum state of the entire universe in a single shot. I mean, talk about ambitious. This was their shot at a theory of everything in a nutshell. But when they wrote it down,
something absolutely shocking happened. The variable for time, the little t that you see in pretty much every other equation in physics, it just vanished. It completely canceled itself out of the equation. What they were left with was an equation that describes a universe that, from a kind of God's eye view, is completely static, frozen, timeless.
And this leads to a truly mind-bending question. If the fundamental equation for all of reality has no time in it, what in the world does that say about our experience? Our experience of a dynamic, evolving universe. How can a static block universe possibly contain the story of our lives, that feeling of flow of the past becoming the future? Does anything on the deepest level ever truly happen? This whole frozen formalism problem is a huge clue. It suggests that, just maybe, we've been thinking about this whole thing completely backwards. Maybe space-time isn't the fundamental stage of reality. Maybe it's something that emerges from a deeper, non-spatial temporal level. Let me give you an analogy to make this a little clearer. Think about water, a single H2O molecule. It isn't wet, right? It doesn't have the property of wetness. But you get enough of them together, interacting in just the right way, and this collective property of wetness just emerges. So what if space-time is like that? What if the fundamental ingredients of our universe aren't by themselves spatial or temporal at all? This leads to a stunning idea called geometrogenesis, which literally means the birth of geometry. How cool is that? Leading theories like causal set theory and loop quantum gravity propose that at the most fundamental level, there are just these abstract atoms of existence. And these things aren't in space or time, they create space and time through how they interact. They connect based on quantum rules, forming this huge, vast network. And when you zoom out from this incredibly complex pixelated network, the smooth, continuous, four-dimensional space-time of Einstein's theories emerges as a large-scale approximation. But okay, where does our experience of time's flow come from? Well, one of the most fascinating ideas pioneered by Don Page and William Wooters links it directly to quantum entanglement. The idea is that the universe as a whole from the outside remains in that static, timeless state. But for an observer inside the universe, like us, our entanglement with our surroundings, with our clock, creates a correlation. And that correlation is what we perceive as time evolution. In a weird way, you could say time is just the universe observing itself. So this leaves us with a pretty profound final question. Our journey has taken us from the familiar stage of space and time to a place where that stage just dissolves into a network of pure information, pure relationships. If space-time is just an emergent illusion, a collective effect of some deeper reality, then what is that reality truly made of? And that is perhaps the deepest mystery in all of physics.